you about Dessin d'enfant and the theory itself, and just let you know what it is. So the first part will be more about the objects I study, and then I will tell you how I count them. So the plan is as follows. At first I give you introduction with some history of the topic. Then will go through the main part of this theory. It is based on the equivalency of three languages that we can speak of the same objects. And then I'll make a little remark about Galois action. So, and the next part will be map enumeration, as was announced. The foundations lie maybe in the 19th century, when Felix Klein studied his objects. He studied the coverings of Riemann sphere. Maybe you know his Klein quartic. And also some early protoforms appeared in the works of William Hamilton when he studied Hamiltonian paths on icosahedral graph. But that wasn't the theory. It was just some marks of these outstanding researchers. And the whole situation changed in 20th century when Alexander Grothendieck published his Esquisse and program. This was really ambiguous program, and he used Bieley theorem to rediscover this theory and to develop it. So there are three equivalent ways to study Dessin d'enfant, and these are as follows. The one is combinatorial topology, the next is algebraic geometry, and also we can study it through group theory. And I think that theory of Dessin d'enfant is unique because it is unification of all these theories that existed through all of the history of mathematics. And to be more rigor, these are equivalent categories. So for details, I can now give the first definition in one language. So we start with the pair, where X is a topological surface. It is uniquely defined by its genus. It is compact, oriented, two-dimensional. So we can draw just the sphere, or maybe the torus. And then we have a graph embedded in this surface. It is bicolored. That means that the adjacent vertices that are ends of the edge, they are of different colors. There are two colors, black and white. So
you color vertices, not edges?
Yes, vertices. I'll give an example. Maybe I can draw just the segment or add more edges. And the important aspect is that if we cut our surface using the lines of our graph, we get disjoint union of connected we get just union of disks. For example, here, if we cut, we get just the thing that is homomorphic to disk. And this is not this dessin d'enfant, because if we cut here, make the hole, we don't get the disk. So to make it the dessin d'enfant, I will do this. And now we have dessin d'enfant, because actually it is, as it is well known, this thing. So the graph is the sides of square, and I glue them by standard gluing. So this is our.
The vertices in this example?
We have only one vertex, because this gluing to this is glued to this glues to this. And
but then each edge connect vertices of the same color.
Yes, and in that case, we always add the white vertex at the center of each edge, and then it is
artificially add such vertices.
Sometimes we don't tell that, but it is we imply that if we draw only black vertices. And this is the beginning.
The edges of the graph intersect, or it is
They cannot intersect. Because we want to cut our surface and get the union of disks. This is just one disk. This is homomorphic to one disk. Also, we can study the dessin d'enfant by coding it with permutation. So actually, dessin d'enfant is the triple of permutations, and they should satisfy the following rules. So their composition is identity, and the group generated by them is acts transitively. So I'll tell you how it can be obtained in the terms of our graphs. So consider this graph.
Why don't we say that we have just two permutations?
Because I'll tell you.
I also think about this, because the last equality determines.
So the first, what we do, we just put numbers. We enumerate our edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first permutation will be for black vertices. This will be phi. I'll write it explicitly. The next permutation will be for white vertices, and the third permutation, this was sigma, sorry, phi, is for the centers of faces. Faces is is that components that we get when we cut our surface. So this is the face of a map. So I'll write the permutations. Our surface is oriented, so, and then we just we take our vertices and see what edge go to what edge when we go around this vertex. So we see that with this direction. We see that 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is this. Then we take the next edge. We see that 4 goes to 5, 5 goes to 4. And here 7 goes to 8, 8 goes to 9. And that's all. We have 9 edges. For white vertices, 1 goes to 4. Then 5 goes to 7. This is involution. 8 remains.
There is 5, 6, 7.
Oh, I'm sorry. Yes, this is 5, 6, 7. And 2, 9, 3. And then we should go.
Why is this 8 is fixed?
Because when we go around the vertex, it is actually monodromy.
Because this is a vertex of degree 1.
Yes, and this is the group for. This is the monodromy group. So we go around.
It's like black vertex below, where is 6, right? And so
6. Yes, it is fixed. And when we go around the face, we go through, we take only half of the edges that are adjacent to face. We see that 1 goes to 5 because we miss 4, and 5 goes to 9. Then we have this loop. We take only one edge. We take this because it was not in this face. And the other is the cycle. 4, so 3, 8, 6, 4.
Do you have another brighter pencil?
I'll try new one.
Anton has.
Thank you. So this triple of permutation is.
How will we construct the last one?
We have faces. Faces are bounded by edges. So we take only half edges. So we go through face, but we miss when we go. We miss half of the edges. We take 1, and it immediately goes to 5. Then it goes to 9, and 9 miss 2 goes to 1.
Such a strange rule. Why do you ignore all faces?
Because we want to satisfy the equality sigma, alpha, phi is identity.
I'm sorry, and for are the 4 goes to 7 or not?
6 goes to 1, 5, and 9, but not 2, 4, and 6.
Yes, this is the right question.
Well, I understand this.
Which half?
For each edge, we we prescribe it only to one side. Each edge goes to, well, you may look at it as an arrow from black vertex to white vertex, then it goes to the left. It goes to the left face.
And for all faces, we have only from black to white for some orientation.
Yes, for every
correct?
face we have every second edge.
Is the composition identity, like if I apply from right to the left, phi of 1 is 5, by alpha 5 goes to 6, and by sigma I think 6 is fixed.
Maybe
So you claim that we don't have this equality?
or maybe the order is maybe it's phi alpha sigma.
Such an exciting topic. All people participate in this.
Maybe we need to choose another side.
Maybe I have a mistake, but the idea is that we should go, when we do this composition, actually we go firstly around black vertex, then we go around white vertex, and then we go around the face, and we should get the same edge.
So multiply permutation from the left to the right.
Yes, maybe I think the technical details may be missed now, but I want you to see that equality in terms of my drawing. That we go around black, then go around white, and then around face. And we get the identity. So actually, there are two permutations that code that tells us the structure, that tells us something about the structure of our graph, because the third permutation is expressed in terms of first and second.
Let me answer to Nikita's question, because this is specifically Russian talk. If some equality is hold, then it is illustrated by example. There is no guarantee at all that in this example, this identity will hold. But this is some specific, we are sorry, this identity is true forever.
And
Sorry, I don't understand still. All right. Let me check. It's on edge where is 3 right. What will happen is?
What you want to see how edge is
Yes.
rotated?
Yes.
So maybe I'm mistaken with face permutation, but
It doesn't matter.
okay. So we go.
Yes.
We go.
Start from edge number 3.
Okay. So we have our direction. We go to this was 1. So we go to 1. Then 1 goes to 4. And
And then inside the central face, it goes to...
and then 4 is adjacent to outer face. Outer face, it is on the Riemann surface. So if we cut, it is so they're actually not plane. We imagine them on sphere. So if we cut this figure, we get disk, and this will be the third map face, and it has a permutation that take this edge to this, and we get the identity because this edge stays here. And these permutations, they act on the set of edges of our graph. And the quality that the group acts transitively, generated by this permutation, it means that our graph is connected. So then I will present the third.
Question? Maybe.
Yes.
Well, if we take a graph of two edges connected, which make a circle, then sigma and alpha are trivial. So
Let us draw the picture.
Okay. So this is this. So our permutations will be just
I'm sorry, yes.
transpositions, and for
I just it was surprising to me that transitivity is equivalent to the connectedness of the graph.
because it's like we go through our graph, like from this to this, when we rotate and go through edges and find the path that connects our vertices. That is transitive action, because we rotate.
So by surprise, in this simple example, this equality holds.
Yes, because two involution give us what we want. So let me introduce the third language we can use to study our drawings. That is Belly pairs. And this is more from algebraic geometry. Belly pair.
This is second language.
Third. Because we started with topological surfaces and graphs embedded on in them.
This is language number 1.
Yes, this is language number 2. We study permutations. We study groups. We study the group that is generated by this triple of permutations. We call them cartographic groups, and they're really important and interesting topic to study. So then we go to the third language, where we take X, which is a Riemann surface, and we take meromorphic function that is unramified outside 3 points, 0, 1, and infinity.
And may you go one slide back?
Yes.
So the claim is that any such triple determines you such a picture with a graph?
Yes.
Because it's clear how to construct such a permutations when we have such a graph. And conversely, if you have such permutations, what to do?
If you have such permutations, you know you have black, white, and faces. So you have here 4 cycles. 4 cycles. 1, 2, 3, 4. That means that we have 4 black vertices. Then, so we do it by cyclic decompositions of our permutations. Here we have 4 white vertices and 3 faces. Then I'll draw these edges and recover the structure of my Dessin d'enfant.
You will obtain some graph, and the statement is that this graph can be embedded into some surface such that the complement is a union of discs.
Yes, that is that is because we have this permutation. that because our surface is glued out of these disks that are faces.
And for example, if I have sigma is a cycle, or just one cycle, and alpha and phi is identity.
Alpha and phi cannot be identity because their product should be. You can do it yourself, maybe like at home. Just do some. You can take any permutations, and then you can draw your own graph, and you can easily see that it lies on some surface, and we can find its genus by Euler's using Euler's characteristic, because we know the number of vertices, edges, and faces. So the most intriguing part that the whole theory started with, like series theory, that is this, the connection with the Bailey pairs. So if we take Riemann surface and meromorphic function on it, we can draw our graph by taking the pre-image of the segment from 0 to 1 on the sphere. So we have the covering. Actually, it is the covering of Riemann sphere. It is unramified outside these points 0, 1, and infinity. So black vertices are preimages of 0, and white vertices are preimages of 1. And each face has a center, which is a pole. It is the preimages of infinity.
And what are edges?
Edges is this.
On the picture it's clear, but formally, how to reconstruct edges having this?
We have function. I imagine that you have a function of degree 3, for example. Then this, if we take an edge and don't take the ends of an edge, we get just 3 preimages of this.
Edges are just preimages of the segment.
Yes, and the covering is this is the point of ramification, and this is if we take the preimage, it is the preimages of 0 are points where the edges intersect. And our group that is studied, it actually describes the monodromy. So if we go here around 0, here we go around this vertex and get another edge. So we see how monodromy acts. And one of the most important theorems that lies in the basis of the theory, and without it, it couldn't be developed, it is Bailey theorem. It states that a Riemann surface can be realized over a field of algebraic numbers if and only if there exists the covering that is unramified outside these 3 points. And in such case, meromorphic function, we can choose it to have all coefficients will be defined over algebraic numbers. And I want to mention that the important thing that here is that it only we can choose f to be defined over this field. Not all f functions are defined over this field. We can spoil any good function. For example, if we take this good function, we can spoil it by just adding p. But we can choose it to be defined over algebraic closure of Q. And what is why it is important for us? Because we saw that if we have a Dessin, it actually it is embedded in surface, and it provides the structure for it to be the Riemann surface. And we want to know what Riemann surface arise in these questions. And the answer provided by this theorem, and we know that the Riemann surfaces that we study are exactly those who are defined over a field of algebraic numbers. And also there is a corollary of this theorem that the action of absolute Galois group on dessins is faithful. So for each element of this group, there exists an element that do not stay under the action of this element. And it is actually was very surprising for Grothendieck, because this group is really, really mysterious for mathematicians. We do not know its structure, but we can see it with our eyes. And the Grothendieck was really shocked by this, and he wrote that any child drawing scrawled on a bit of paper gives a perfectly explicit example to really, really serious mathematics, because in earlier ages, Grothendieck studied more objects in most of their generality, and then he saw that we can see them in so simple objects. Also, he stated after that he was amazed at this with the same impact when he gets to know the definition of a circle when he was 12 years old. And what is about Galois action? This Galois group, we do not know its structure, but we can see it by the action on Dessin d'Enfant. We can see the orbits of this action. So some dessins are making the orbits of the section. We can study the action by seeing the orbits. And what is an open question now is to find all the invariants of the section. We want to answer the question how to distinguish elements in different orbits. There are several invariants. For example, passport of the Dessin, genus, and many other, but the full list, and we don't even know is it finite or not. Then I will turn to more specific question. The whole theory is really, really big, and it is really hard to describe all of its achievements through all of that, through all the years that was developed. So I chose to tell you about one specific area that is my topic of research. When we define objects, so what mathematicians do, they count them. And in that case, we don't simply count, just taking one when we get the objects, but we count them with respect to optomorphisms. So this is just observation.
But what is x and another x here?
Let x is objects. X is just some set of dessins. It can be defined by some parameters. The parameters may vary because it depends on the task. For example, maybe the genus, the number of edges. I think I think further you will get to know. And X are objects in that set.
X are concrete pictures, concrete graphs.
Yes, yes. But some graphs have optomorphisms. For example, if we take this graph, it have an simply optomorphism. We can see it because we can rotate it and get the same drawing. So,
but you have there's a Galois group, right? So let us write down this group. Galois of Q bar over Q, right?
No, we don't study now. It is like the study of. I do not now stay on the Galois group. I mention it because it is an important part of the theory, and it was the Grothendieck's aim to study the Galois group. But actually, we failed, and we don't know how it acts. But here, in my studies and further speech, the action is just of this group when edges are rotated. But the optomorphism can be defined in 3 languages. In one language, it is permutation that commutes with all this.
This will be automorphism of the same graph, and you would like to have different graphs. One graph is moved to another by your action, not? You always have the same graph.
If you I want to define the automorphism group of a graph. In one language, it is automorphism of underlying surface, that we have sphere and we can rotate our sphere in one language. In the second language, if we take permutations, we should take some, our edges here are labeled 1, 2, 3, 4, 5. And I can enumerate it in new way. 1, 2, 3, 4, 5. But in the first, the permutation was 1, 2, 3, 4, 5, and then I renumerated it. The permutation itself stays as it was earlier. That means that we get the same edge.
So all permutations, sigma, alpha, and phi, should remain the same.
Yes, because we should get the same dessin. If we renumerate edges, that means the rotation. We get the same.
And how to understand that I can renumerate edges in this way, but I can't, for example, just swap first and the second edge.
We look at permutations.
Yes, we look at the permutations. We should get the same permutations.
And what is this letter?
What letter?
This, I don't know how to call it. Not this one, but on the other blackboard.
He.
Okay. This
X.
I or X. So what is this? If you have the same graph, you don't have many graphs. You don't have a family of graphs.
You asked me what is the automorphism of a graph. For example, I have some graphs. This graph, this graph, and this. So in my sum, they are not. I do not count them as 3, but I count them this way. So we see that here 5 automorphisms, 5 rotations. This we count with this, so 1/5 plus 1/3 plus 1 plus a half. Plus, for example, I can draw some dessin without automorphisms. It will have automorphism. I tried to spoil it. So this dessin don't have automorphisms. It has 5. So in the resulting sum, we won't have 4 of them. We will have this quantity. So
so this is some family of graphs. This is not orbit of one graph under some group action.
No, just some set that is defined under some parameters. And now I will provide you with some examples. You know some example from school, maybe from the first course of your university. It is simple example. It is well known that Catalan numbers enumerate the rooted trees. Trees are the simplest example of dessin d'enfant. So the parameter here is the number of vertices. But this is simple, and I do not give you a proof because I think that it is clear to you. The proof is just by bijection. And then I want to solve this problem. Compute the number of one-face maps. That means that they have one face of genus G with n edges. Here we have two parameters, genus and the number of edges. So in other words, it is equivalent to enumerate the ways to obtain a surface of genus G by gluing the two and on. So I will draw it. Have we eraser for? So how to glue? We take n is equal to 2, and how to glue the square? There are 3 ways to glue the square. This with this with this, and we distinguish between that case and that case. They are obtained from each other by rotation. Here we get the torus, and I already have drawn it. Here we have sphere, and here we have the same. So we get 2 surfaces of genus 0 and 1 surface of genus 1. But we want to study these quantities for arbitrary n and g. For this, we introduce the sequence of polynomials, where the first sum is taken over all possible gluings. V is the resulting number of vertices, and we can express it in terms of the number of edges and genus by Euler's formula. This is the second equality. And then I consider the exponential generating functions, and the theorem by Harrod and Zagir states that this generating function is as following. And this is really interesting result because it was obtained with the use of matrix integrals. And matrix integrals were earlier used by physicists when they were studying gravity. So this is the part of mathematics where physics came, but for Harrod and Zagir in their theorem, it was just the part, the step in their calculation of Euler's characteristics of the field of the moduli space, and by this generating function, we can obtain the recurrence relation for these numbers. Another proofs of this theorem they exist too. We know a combinatorial proof, and we know some algebraic proof with the use of representation theory. So I want to show you the table for these quantities. You see that the first column, you can see that this is exactly the Catalan numbers. Catalan numbers, I mentioned them. They enumerate the rooted trees this is exactly the ways of gluing the two n-gon to get the sphere. So this is the generalization of that formula. And if we sum the if we sum our if we sum overall, we get this quantity because it is the number of ways to choose the pair of the sides of two n-gon to glue them.
And this picture corresponds to which number? You have this picture, right? So
yes. So this is.
So this is reflected
And
in this table where
n is equal to 2. We we see that the second line in our table, 2 dessins of genus 0, 1 dessin of genus 1.
so you have 2.
This and this of genus 0 and this of genus 1. And the next simple example will be Cayley's formula. Maybe you also know it, that the number of labeled trees on n vertices is equal to n to the power n minus 2. This is, the proof is by Prüfer's encoding. There exist another proofs. And it is simple formula. But then we generalize it and obtain the TAT formula. He obtained it in 1964. We know the weighted number of bicolored plane trees. And what is parameter here is the passport. Passport of the Dessin is the valency of its vertices, black and white, and its maps. So here we see that there are P1 vertices of degree 1. The first is for black. P2 vertices of degree 2, and so on. For white vertices, Q1 vertices of degree 1, Q2 vertices of degree 2, and so on. And we see that that this map have only one face, that is of degree n. That means that it is plane, because if we draw something on the sphere, we get only if only one face, then it is plane. And the number is as follows. So for the next generalization, I want to to tell you about the result of Goupil and Schaeffer. They used more exquisite techniques to get the quantity for the maps of given genus and given passport. So before it was for plain trees with the passport, and here is for any genus. And what is important for us who study Dessin d'enfant is that the passport is invariant under Galois action, and this is the reason why we want to know the quantity of dessins with a given passport. So now it is the end of my talk.
And what are you doing in this regard?
I consider this the specific one. I have a set of dessins. I can write the passport that I study. So my passport is this is for black. This is for white, and this is for faces. So we have this series of objects. And I have one parameter k here. And I want to know what the quantity of these objects for a given k. And for example, for k equals 2, there are two of them. I have two realizations of this passport. Each passport may have more than one realization. Here we have two. So
there is versus of black color which is connected to
the passport tells us the number of vertices and its valences, its degrees. If k is equal to 2, we have one vertex that is 4. Here it is here, and here it is here. One vertex that is 3, and one vertex that have degree 1.
Excuse me, is it possible that two black vertices are connected by an edge?
No, because they are.
but they are connected.
When it is not specified, I draw the white vertices in the center of edge. And I study the and I try to enumerate them, and the hypothesis that this quantity is given by this beautiful formula for me. For if we fix n is equal to k, this is the sum of odd divisors of n. We for fixed n, I can the hypothesis that this quantity is this, and I try to prove it by doing some recursion formula by constructing the coverings. So I'm on my way.
So this is some combinatorics. You compute some pictures.
Yes, but also when we study something, we can use other languages to study something, to study other objects. So it is not pure. My question is more combinatorial, but specialists in this area, they use different languages and reformulate questions from one language to another language, and one theory may become more rich by the use of other theory, and in the opposite direction.
Okay, any more questions, comments, suggestions how to draw pictures? If not, then many thanks to Veronika.